So, the first one with the Rubik's Cube, uh, this one actually started out just how can you use AI to solve the Rubik's Cube? You just give a description. This is what the cube looks like. This is how it moves. And then from there, figure out a solution. And so not just for the Rubik's Cube, but, other puzzles as well. The algorithm goes, here's the description. Here's what we want you to get it to look like. And there's an algorithm out there called A-star search. And this goes back to 1976 or 78. And so this was initially developed for robotics, but works for really any pathfinding problem, sequential decision-making problem, where you need to find, deterministic ones. You need to find a sequence of actions from some starting state to some goal state. For these, pathfinding problems. But the key is you need a heuristic to guide it. So, this direction seems more promising, that direction seems less promising, to kind of prioritize where you're going to look. So the heuristic part is what often people will use domain-specific things they know about the puzzle to come up with a heuristic and then put it in A-star search, and then it's able to solve the problem. What we did is we used deep neural networks and dynamic programming, which is used a lot, really the basis of a lot of reinforcement learning algorithms. So this deep reinforcement learning to learn a heuristic function just based on the description of these puzzles. You learn a heuristic function, you put it into A-star search, and it's able to solve these problems. And then a lot of times it's able to solve them in the most efficient way possible, meaning using the fewest number of moves possible. And so this thing I was really excited about because it showed that, this is very much related to resource consumption. So if you want to synthesize a molecule, you want to do it in a way that is going to not waste, resources, things like this. So, I was really excited about that. But the thing is, explaining such an algorithm to a human, the most efficient algorithm possible to solve the Rubik's Cube probably wouldn't be feasible. So how do you actually explain this to a human? And this is work that is ongoing, but some really early results we got. And let me actually go over the algorithm, just high level. So we add in the ability to describe the Rubik's Cube or certain instances of the Rubik's Cube using logic. And we want to find a logic program that can solve the Rubik's Cube. And the reason we're looking for a logic program is because you can define logical predicates that are really easy for people to understand. For example, there's some cubelet and this sticker is on the yellow face or something. We can understand that. And so you can say, here are the building blocks for your logical programs. These are all things humans can understand. Compose them into a program that solves the Rubik's Cube. And so again, this is an algorithm that's guided by a neural network, except you're looking not just to solve one instance of the cube, but all instances of the cube using this approach. So this program, any instance you give it, it should be able to solve the Rubik's Cube. So, we're starting like really basic. We even just started with just get one little cubelet, that has two colors, two stickers on it. Just get that in its correct position, just one, and explain what that algorithm is, which seems pretty simple. But the algorithm behind actually doing that, a lot actually went into it. And the solution it gave was actually more simple than what I was thinking, because I was thinking like, you get one of the colors in place, get one of the colors in place and then move the other, you move the face that is in place, you turn it so that the other one's in place, which is pretty simple. But that part about get one of them in place was kind of ambiguous. And I was like, I don't know, just get one of them in place. But the solution it came up with was, if one of the stickers is a certain direction away from the sticker it matches, you move it in that direction. No matter if it's one in place or the other one, none are in place, you just move it in that direction. Otherwise, one of the stickers is on some face, doesn't matter what face. But if that isn't the case, one of the stickers is on some face, just move that face clockwise or counterclockwise. And then that's it. And you would have solved it. And so there are actually only two things you really need to take into account.
Oh, interesting.
that was a lot simpler than what I was thinking about. And this is
Yeah.
just like for this really simple case.
Right.
So I was really excited about that.
Oh, that's excellent. Yeah, because it seems quite crazy. But I didn't think that is the solution is that simple. It's
Yeah,
pretty
it's
good.
it's something like anyone could do, but then
Yeah.
even just explaining it was kind of, that part about just get one of them in place, just
Yeah.
one of them to match, I mean,
Yeah.
was just kind of like I just would wave my hands. But this one says it in a really simple way that I don't think I would have thought of.
Really nice. I like that.